all things. So the food, like the intellectual ones. To be too quick is not a good thing. Although present-day world pushes us to be quick and fast, but that is detrimental for some things. Well, a lot gets done, okay? In the past, much less was possible. And this lot that gets done, should go to benefit people. So I'm not criticizing the modern world just because I'm an old man. I think that we always go towards better things, that the past is not better than the future. So, but still, some things need time. That was true in the past, and it is true also today. I see it with my many students and so on, collaborators, okay? And so don't worry, okay, about what is happening in these classes in such a short time. Of course, if you have questions, just get back to me. And in the tutorial hours, that we have 2 tutorial hours also today, maybe there is a chance to discuss things more. Now, the amount of material I would like to cover this morning is not too much, so maybe we have time for some exercise that then you implement in the tutorial hours, okay? We'll see. We do what is possible to do. And what is not possible is not possible. Okay, so I start now. We had 6 academic minutes. I don't know, maybe other people are coming, but perhaps I should start, right? So if they come, in any case, there is the material. It is all in print, what we use, what we do today. Yeah, unless there are questions directly that I can try to answer before I start today's class. Or if questions come along, you just stop me and say, okay? Okay, so let me go back to where we stopped yesterday, which was this, the definition of the evolution of a probability measure, okay? So we said that if mu is a probability measure, maybe this probability depends on a time t. And this probability measure can be used in various ways. One is to attribute a weight to subsets of the big space, which is called phase space. Okay? And that we define it as we would do with the mass of a fluid. Now, if you keep this in mind, it will help you to see through the calculations, because some calculations get a bit involved. But you keep in mind this, if it helps you, okay, if you have physical intuition about a fluid. A fluid, for instance, a gas, the air in this room, okay? Yesterday I spoke about the water that goes from the glass into my stomach. Okay, the same thing. When the winds blow, air moves around, okay? And it carries with itself its own weight. Yes, air is thin. It's not very heavy, but it has a weight, okay? It has a mass. It has a mass. The weight comes from the force of gravity, but the mass is a property of the molecules of air. So when they move around, maybe they get compressed because there is high pressure, and then you feel hot, okay? Or maybe they expand because there is low pressure. So the volumes can change, but the mass remains the same. The volumes can change and can move from place to place. Okay? Now the winds are blowing in Delhi, hopefully. They're not blowing here. But the perturbation may move. Okay? It comes here. So the mass has moved. It has changed shape, but the mass remains the same. This is the idea. Okay? This is the idea. We think the probability is like mass. And mass at time t in a location E is the mass that at time 0 was in the pre-image. Okay? This is the meaning of this abstract formulation, but in the end, it makes sense. Why do mathematicians develop such a formula? Well, because whether they want or they don't want, they think about the real world. Sometimes you hear that mathematics is a beautiful abstract thing. Okay, it is an opinion. Okay? I think that it is that to be totally abstract is impossible, because we are made of flesh. We touch things with our hands, and these are the only things that we know. Nothing comes out of nothing. This is an old saying of the Latins. Okay? Ex nihil nihilo. Nothing from nothing. So we always have something in mind. And in fact, mathematicians give names to these things. Okay? And you will find that this is called mass in mathematical textbooks. But if it is the probability of temperature, certainly there is no mass, right? But we call it mass because that helps our intuition. So this is the meaning of the formula. Keeping that in mind, maybe that calculations look more reasonable. Okay, so this will be equal, by definition, to the integral over the set E of the probability at time t. And this will be equal to the integral over the set phi minus t e of the other probability, d mu 0. Okay? Now, we introduced the characteristic function that is 1 when you are inside E and 0 when you are outside. So you can write this in a more general form, which is integral over the whole phase space. So this can change, this does not change. Over the whole phase space of a given function, chi e, the characteristic function evaluated at the point, okay, d mu t of x, and this will be the integral over the whole m, you see it's the same, of what? Of chi, the characteristic function. Now this is based on phi minus t e of x, and this is d mu 0 of x. Okay? So these are things that you can use. Now, suppose that you are not, then when you do an integration like this, you have a function and a probability. What you obtain by definition is an expectation value, is an expected value. So we can write this also as expectation. Now you see the difference between E, a subset, and this thick E is expectation, okay, at time t, of my function chi E. This is the definition of expectation, is the integral of my function with respect to this measure. Well, you may wonder, why do I call it E? It's not me. It is probabilistic terminology. It means event. That is the probability of an event. Which event? The event of x being inside E. Okay? It is an event. What is the probability that temperature is between, today, I don't know, it feels around 10 degrees, something like that, 8 degrees. What is the probability that it is between 8 and 10? Okay, the event E, in that case, E, would be the set 8, 10. Okay? And M will be, if we want to exaggerate, the real numbers, assuming that temperatures can go from minus infinity to plus infinity. Luckily, it doesn't happen. But in some places in India, it seems that the upper bound doesn't exist. Being in the south, in some pretty hot places, even in winter. Okay, so also this helps. Now, if you integrate your function, whatever function, a function in a given function space, often we take L1. Okay? Although it is a huge space. You get the expectation value. So here you have the expectation value at time 0, because the probability is the probability of time 0, of a different function, chi phi minus t e. Okay? Now take a more generic quantity, observable as we called it, okay? We call it O. And O is just a function in our function space that goes from the phase space to the real numbers. Okay? Now we can take the expectation at time t of observable O. By definition, it will be the same thing. It will be the integral over m of O of x d mu t of x. Okay? And as we did that, we could have taken the expectation at time 0 of the same observable O. You see, there is a difference between this and this. This is an expectation at time 0, okay. This is expectation at time t, okay. So like here, at time t and at time 0, but of two different functions, chi e and chi phi minus t e. Okay? Here I'm taking the same function. So in general, these two are different. Okay? They are not the same. Now, you understand the sequence of equalities that I have written on top? They correspond to the fact that the mass is conserved. So we are saying the probability is conserved, even if it moves around. That is the meaning of this sequence of equality. But if I look at the expectation value of temperature today and of temperature tomorrow, they will be different in general. Okay? So you don't have that sequence of equality. So if you have the same function, but you change the probability, then the expectation may be different. It doesn't always happen. Okay? It doesn't always happen. It may happen. You see the eraser on the other one? By the way, Sivaraji, these markers are very nice. Yeah, right. They're good. So it could happen. It could happen that the expectation remains the same. Et of O is equal to E0 of O. If, okay, if this is true for every observable in our function space, let me call it F. If it is true for every t, say, could be real, but could be integer, like in the case of the logistic map. Okay? If it is true for every observable in the space that you have chosen, and for every time t, then okay, it is true also for the characteristic functions of the sets. Okay? Then what you have is that E0 of chi E by definition is equal to Et of chi E. Sorry, by definition. I mean by the hypothesis. Because chi E is a function. It belongs to the space. Okay? But by definition, Et chi E is equal to E0, you see, go back, is equal to E0 chi phi minus t E. So now you have this equality. Okay? If it so happens, okay, which I told you is not true in general it will not happen. But if it does, then you have that the expectation of the characteristic function chi E. But what is that? That is mu0 of E. Okay? Expectation of whatever time. Chi E is its measure, its probability. So this is equal to this. And this is equal to its to the measure of phi minus t E. Okay? But mu0 of phi minus t E is equal to mu t of E, which is here. So you know what happens? That the probability of E does not change. So if expectations don't change, probabilities don't change. And it is two-way. Of course, if the probability has not changed, the expectation will not change, because you do the same integral. Okay? If the probability here is the same probability that you have an earlier time, okay? If the probability here is the same that you have here, this integral and this integral are equal, because the function is the same. But it goes also the other way. If expectations are the same, don't change in time, then probabilities must be the same, provided this equality holds for all observables. And all observables means for all subsets of the sigma algebra that you have chosen. Okay? So things go this way. They can go both ways. There is one that is more mathematical way, and there is another one that is more physical, if you like. The physicists will like to look at the observables, because they are the things that you can measure with measurement tools, with a thermometer. Okay, so they will choose the function space. They will tell you what are the quantities that they want to measure, which means the quantities of which you want to compute the expectation. And mathematicians are open to all possibilities, but they will not dislike the idea of looking at the probability of the event rather than at the expectation values. Okay? But the two things are perfectly parallel. I choose a sigma algebra, which is a set of events of interest, or I choose a function space. You see in this sequence of equalities that can be connected to each other. Also because the characteristic functions, linear combinations of characteristic functions that are called simple functions, are dense in the space that you have. Okay, so it is very much entangled. You choose what? You choose what? Even mathematicians, however, will agree, and we see in a moment, that it is still better to work with expectations than straight with probabilities of events. Okay? Because events can be, even if you have chosen a mild sigma algebra, they can be quite ugly to look at. Okay, like fractal sets, or quite beautiful. That depends. But if you plot them on a computer, you can see beautiful pictures coming out of fractals. If you have to do calculations with fractals, it can be quite complex. And of course, some of our friends are very much experts of fractals, right? Sivaraj. Here also. So far from me saying that they are ugly, it was just a way of saying, you know, it's a complex object to deal with, not very simple. Expectations are simpler. Expectations are simpler because they are the result of an integral. And you know that when you integrate, you smooth out things. You make things easier. Okay. So this is more or less a summary of where we were yesterday. But it was good, I think, to repeat it. So when you have that mu0 of E is equal to mu t of E, we speak of invariant measure. Okay? Where did I put the mark? This means mu t equals mu0, then you can just call it mu, is invariant. Okay? Now, some miracle at times happens. It doesn't always. In fact, it is, if you like the rational within the continuous, within the irrational numbers. Okay? The rational ones are very few, although they are infinitely many, right? And the rest is much, much more. It may happen, however, that there are situations in which, too big. I know.
Second pen process. Pen. Select the pen. Just take it. No, in the same. Yes.
You want to come here, tell me?
Yes.
I don't know what to do.
No. Yeah, in the marker itself. Yesterday only we have done this. So this pen more sharper. Oh, still it is.
No.
No, this size will become very large. Yes.
Yes, okay, very good. Very good. So now, select, let me make a big selection. And then remove. Okay, pen. So, it may happen that d mu t of x equals something like this. Ft of x dx. Okay, where in your space dx, your space you have to decide what it is. Okay, if you want to be mathematically precise, you better choose a manifold, a differentiable manifold. Okay, so like a surface embedded in a larger space. But in those coordinates on that manifold, but Rn is also very smooth, is flat. Okay? This is called the Lebesgue measure. Okay? It is the volume measure. And if you have that this is the case, okay, to be a probability, you have to have that the integral over all m of d mu t has to be equal to 1, it will be integral over m of ft of x dx to be 1. Okay? The probability is always non-negative. So you also require ft of x to be bigger or equal than 0. Okay? So this is called a probability density in probabilistic terms. You see, the notion of mass comes back. It is called the probability density because the mass then is given by the density times the volume. If you integrate over the whole volume, you get the whole mass. And the whole mass for probability will be equal to 1. Okay? And for those who do statistics, that corresponds to 100%. Okay? So that we saw it yesterday. Okay? The measure of any set is a number between 0 and 1. And it is defined this way. So when you have this situation, you say that the measure mu t is absolutely continuous with respect to the Lebesgue measure. Okay? And more speedily, people can say that it is a regular measure. It is regular. Okay? Now, this situation is very rare. But it does happen in very relevant situations. So it is important to consider it. In particular, in the description of physical systems in an equilibrium state, then you are in these situations. And you have the measures that are called ensembles. Maybe you have heard about the microcanonical ensemble. It is the simplest one. It is uniform. Now I'm exaggerating, okay? Here one should be much more refined, but generically it is a uniform distribution, so it is like the Lebesgue measure. It does not have a density that changes. Density is equal to a constant, and is equal to 1 divided by the volume. Okay, so this is the microcanonical ensemble. The microcanonical ensemble describes systems that are isolated from the external world. Okay, so sometimes they are drawn like this. You have a box with thick walls. And through these thick walls, neither matter nor energy can go through. Well, then, this ensemble, this F, okay, and because it is an equilibrium state, will be an invariant F, will not depend on T, then is suitable to obtain a lot of results. There is the canonical ensemble. Please, please. Ooh, good. Good, good. There is the canonical ensemble. Okay, this describes systems that are not called isolated. They are called closed. Closed means that the walls don't allow matter to go in and out, but energy is allowed to go through. So you can give heat, you can warm it up, or cool it down. Then you use the canonical. And then there are generalizations of this that are called grand canonical. In all of them, you have something like this. In the canonical ensemble, you have that the distribution is E2 minus a certain parameter beta times a certain function h that is called the Hamiltonian divided by the normalization that depends on this parameter beta. And then the probability, if this is an h of x, where x can be a very large vector, okay, this is a volume in a very large, in a very high dimensional space, and that is what it is. Okay? If we are lucky, we get to the point of using it. So now, the problem of computing the evolution of the probability can become a little more explicit, because we can look at the evolution of the probability densities. Okay? We look at the evolution of the probability densities. So still, the definition is what we used to have. Okay? What we need is that the integral over a certain set E of now ft, it changed color. Okay. Ft of x, and now it went back. It has its own life, its own intelligence. I don't know if it is artificial or natural. Okay, so you have this, which corresponds to this integral now. Okay, integral d mu t is that integral, because d mu t is this. So this has to be equal to the integral over the pre-image of f0 of x dx. Okay? Now, if you think the pre-image, by its definition that I gave you yesterday, are all the points that in a time t will go inside E. Okay? This is all the points that have a certain mass that after a time t are found inside E, by definition. Okay? If you want, I can write the definition again. Over here. So, the pre-image, we'll do an exercise today. We'll do these calculations explicitly, and then you implement it in MATLAB, is the set of all points x in the phase space such that phi tx belongs to E. Okay? This is what it means. So, the points that are in here are those that after a time t are here. Well, then we can do, if we know this transformation phi minus t, we can do a change of coordinates inside the integral. Okay? We can do a change of coordinates. Let's do this. Let us substitute x with phi minus t y. And we go to the new variable y. Now you know that when in an integral you do a change of coordinates, you have to compute the Jacobian of the transformation. So we introduce the determinant, of the Jacobian transformation, which I call it j minus t because there is a minus t here, evaluated at point y, okay, by definition is the absolute value, okay, of the determinant d phi minus t by dy, okay, a function of y. Let's see if I can do it. Yes. Good boy. Okay. This may be difficult to compute, but in some cases it's not difficult to compute. When it is difficult to compute, ask a computer to do it. And sometimes also computers have their own problems. But at least they always give you an answer. Maybe the answer is wrong. So you have to be careful. Okay? Because computers are used to give, they know that they have to give you an answer. Okay? Sometimes they give you none, not a number. Then you know. Then you know. Sometimes they don't tell you. Sometimes they give you a number and you wonder, what number is this? Anyways, if you have done that, now let us write our integral here like this. Let me see. That one, yeah, sorry, not this one, this one. It becomes the integral of f0 computed now in place of x, I have this. So phi minus ty. I change coordinates, so I have to introduce the Jacobian j minus t of y. And now I integrate with respect to dy. Now the limits of integration have changed because I changed the variables. And so you have to ask, what should I stick there? All right, now think what you should put there. Think. When I have x, I take the points that are in the pre-image of E. When I have x. When I have y, where is y to be found? Huh? Someone said. Yes, almost. This is the pre-image. So you see, this is a point in the pre-image. Okay? So, sorry, it is a point that goes into the pre-image when you take it back. Okay? I also got confused. I apologize. I do it from the beginning. X is in the pre-image. Y is a point that is not in the pre-image. It will be in the pre-image if I take it back. So it is in the image. It is in E. Okay? You reflect on it, but it's like that. Okay? This quantity should be in the pre-image. But then y should be in the set. Okay? I take a point in the set, I evolve it backward for a time t, I finish in the pre-image, so I was where E should be. Okay? But now this is very interesting. Because this is equal to this. And now they are both integrated over the same set. And now suppose that this is true for all sets of the sigma algebra that define the probability. Then the equality of the integrals is the equality of the integrands. Okay? Then you have that ft of x is equal to f0 in the pre-image. Sorry, now y is a dummy variable, right? Y is a dummy variable. It is just for integration. So whether I call it x or y makes no difference, right? It is just a label. So this is equal to F0 in the pre-image of X times J minus T in X. Okay? If this is true for all E, okay? If true for all E in the sigma algebra. If it is true for E in the sigma algebra, in this representation of the space, the sigma algebra is a representation of the space. In this representation of the space, this function is equal to this function. You have to keep this in mind, okay? Because things are a little more complex than thinking about y equals x squared. It's a parabola, it is like that over all points. Okay? When you do an integral, you lose the notion of this fine structure, continuum structure of the space, because integrating you smooth out. Okay? So depending on how finely you decompose your space, depending on that, this equality is easier to obtain or harder to obtain. Okay? And that is why then you may speak about different measures. You may speak about different forms of convergence and so on. Okay? If you want the convergence in L infinity, is harder than the convergence in L1. Why? Because in L infinity, to get equal, you have to struggle more. Okay? Equal means really equal. While in L1, equal means that the integral of the absolute value of the difference is equal to 0. It's much weaker condition, much weaker. Okay? In any case, for us, we have no other knowledge than the sigma algebra, and the functions that we use are those corresponding to the sigma algebra, so this is true. With our level of resolution, a physicist would say. I have a microscope that can look so much finely and no more finely than that. On that level, these two things are equal. And mathematically, it's perfectly correct. Okay? There is no cheating. Okay, so now we have an expression for this. Because we have an expression for this, we also have an expression for the observables. So let me compute the expected value at time t of an observable O. Okay, that is equal to, what did I write? Undo. That is equal to integral over my space M O of x. Now ft of x is f0 in the pre-image phi minus tx j minus tx dx. Okay? It's just using the definition. Let's do another change of coordinates. Now we do the opposite change. Okay? Because now here I have phi minus tx, which I don't like very much. So let me do this. Change to this time I take y equals the forward evolution phi tx. Okay? no. I have x, so I have to do the change of coordinates. Select. Erase. This is. Well, first I eliminate also this. Delete. Then I go back to pen. So x equal phi ty. Okay, here. I want to change from x to this new variable, y, but this time it is defined in the opposite way. Okay, so this change of coordinates will have its own Jacobian, which this time I call jt, okay, because there is a t. So this becomes now equal to the integral. Now watch out, because we are going to obtain in a minute a very important result. Integral over m. You see, here I don't have to worry about the set, because I'm integrating over the whole world that is available. So whether I use one set of coordinates or a different set of coordinates, the whole world remains the whole world. Okay? If I have to integrate over the whole real line from minus infinity to infinity, and I change variables, I still integrate from minus infinity to infinity. Okay? So this is the meaning of this. Now, O contained x, so now it is evaluated in the point phi ty. F0, F0 is evaluated at phi minus tx, where x is phi ty. So I do t step backwards, and then t step forward. So this is just y. Okay, now you remember that yesterday we said we want this group property. It is still there, huh? Did I do something wrong? No, yeah, I can do something wrong. Huh? Don't you tell me. But what was the comment? Phi t compared with phi s, composed with phi s is phi t plus s. You were repeating this, right? Okay. Now s is minus t, and then I have t. T plus minus t is 0. Phi 0 is the identity. Okay? So, whichever way you look at it, you have y. But also think of this. I walk forward in time for a time t, and then I walk backward for the exact same time t. I end up where I started, in the identity. Okay? So, now we have the Jacobian, j minus t computed. Now, this is the thing that you have to keep in mind, and thinking of fluids will help. So x is phi ty. And then, so this is the old function. Now, because I changed coordinates, I have to introduce the Jacobian, which will be, this time, jty dy. Okay? Any question, observation? You want to say something?
As we already defined j minus t of y, the absolute value del of the phi minus t upon del y upon y. So we can put it here.
Yeah, didn't I do it? So, come, show me. I'm not sure I understood what. Let me see in my notes if I did something wrong. No, don't be afraid. Okay, I do wrong things all the time. Come. Because you know, this is also something that I use as an excuse with my students. Because from there, you see things that from here I cannot see.
At that, what I was thinking, like,
Yes.
you already defined it here. So I was just putting it here, like this value, calculating, and whatever we will get, we can put it.
Oh, now I see you want to do more than I wanted. because the y is not the same y. There are two different changes of coordinates. So I'm not sure that you can do that operation. I'm not sure, but I have to think. Maybe you are right. But this y here came from this. And this y here comes from this. So there are two different transformations. Okay? But maybe in the end it's the same. I'm not sure, because what I'm going to get is something trivial. Okay? So then you tell me if it was what you had in mind. Okay? But for the moment, I just go back to what I had. Takes well, anyway, I know what to do. I select this. Then I delete it. And then that frame doesn't touch anything, okay? Now I ask you to think, now for a given single y, which could be what you have in mind. I'm not sure. But here I know what I have. I have a single y here and here, like throughout. Okay? The y is the y. Think what happens if you start. So I am here, a starting point. Okay? My point is y. Here is y, okay? You remember. Here is y. Now I move for a time t, okay? And the mass that I had here, after a time t and doing some wobbling, okay, arrives here. This is after a time t. This is phi t y. So the Jacobian of this transformation, you know what it represents? It represents the factor by which the volume has changed. So suppose it has expanded, it has become like this. Okay? That is what the Jacobian represents. Okay? In hydrodynamics, this is clear. But we use probability as if it is a fluid. We are in a much more abstract and sophisticated space than the three-dimensional space where the glass of water lies. Okay? But the idea is the same. So I was like this back, and I'm like this here. Okay? The factor of change, which is a growth of the volume, is this one. Right? Suppose the volume doubled. Then this is 2. Okay? Now think about this. What do? You start from phi t y. So now you start from here. Now you have a volume. And now you go back by a time t. It is the same points. It's the same dynamics. So if going forward I double the volume, going backward, what do I do? What is the product of these two? 1. Now this can be computed mathematically. But just knowing about fluids, you know that that factor is 1. Okay? We will... Yes? Because they are so good. So, the rule that I described in words... Yeah. The rule is this. Is J minus t of phi t y, okay, is equal to 1 divided by jty. Okay? Yeah, I wrote it correctly. So this is 1, and that allows us to write, I will pull it up because you have already seen, oh, it doesn't want to go? Yeah. This allows us to write the result that I told you is very important. The result is this, is that the expectation value at time t of O is equal to, now you see, this is 1. So here you have the integral of O with respect to the measure J0, mu 0. So this is an expectation at time 0. Ooh, no. I hope. Oh, I'm sorry. Let's now we find out. Expectation of what? The question is expectation at time 0. Yes, because we integrate through f0 dy. So it is expectation at time 0, but of which function? Not of O, but of the function O composed with its time evolution for a time t. Okay? Let me put it more explicitly. What do I mean by O composed with phi t applied to x? Well, I mean, what is there? It is O of phi t x. It is a different function. It is a different function. You know that even with a parabola y equals x squared, if you change coordinates by shifting the origin of the axis, the form is different. Same thing. Same thing. Only in a more abstract, more general sense. Okay? So, why is this result important? What is written here? And then maybe we have our break. Oh, still 4 minutes more to go. We have that the expectation at time t can be obtained as the expectation at time 0 of the evolved observable. So the evolution of the expectation, the evolution of the probability can be cast into the evolution of the observables. I try to tell you all the way along that there is a strong connection between the two things. You define probabilities with observables and observables with probabilities, expectations of observables with probabilities, so these two things have to be related. Now, why is this important? Well, to give you an idea, you have this in quantum mechanics, and it is called, they gave it a name. It is called the equivalence of the Schrödinger to the Heisenberg representations of quantum mechanics. But it's just this, it is a change of coordinates. But why does it get a special name? Because it allows you to compute something that could be very difficult. Because go back to the definition of mu t. It's not easy at all. Yeah, it is easy to write this sequence of equalities. The equalities are true, but now tell me what it is. Very difficult. In particular, suppose that this is clustering on a fractal set. Okay? It becomes a very, very complicated distribution. What happens to f? What happens to f going from f0 to ft? God knows. But the initial state is your initial condition, so you know what is the initial state. So if you can preserve integration with respect to the initial probability, then you are much happier. Of course, nothing comes for free. So you will have to evolve O. But one thing is to evolve O, which means solving the differential equation. And one thing is to evolve the probability, which is much more complex. Okay? So this is a very useful equality, extremely useful, and conceptually important. It says that you can evolve probabilities or equivalently evolve observables, and the result will be the same. Right? This is quite a lot. Now, to conclude this hour of lecture, I want to give you one formula that you can get out of this one. Now, let me see where I put it. We have seen this. Yeah. No, I already gave it to you. So we can have our break now. Okay? Thank you for being patient. Also for your contributions to what I'm doing at the board. And when now we have a break, what time do we come back?
After 20 minutes, yes, after 15 minutes.
15 minutes.